Please welcome.
Thank you very much. My name is Jaewan Kim, and those of you who came from abroad, we have so many Kims. About 22% of the whole population has the name Kim, and among them, majority is also Kim from Kimhae, and I'm one of them. And this Qudit here, I emphasize a D by red color and italicized it because in quantum information science, usually people talk about the Qubit because bit is 0 and 1 of the digital information unit, and that is from binary digit, so it is bit. And then people quantized it, so it became quantum bit, so they called it Qubit. Now, Qubit is not that easy to realize, and then I found a way to make a d-dimensional quantum information unit, and I called it Qudit. And actually many people talk about the Qudit. Here I'm going to present how to make Qudit from some optical, this kind of laser beam. And then one of the operation to entangle two Qudit is easy if we use a nonlinear optical process. So I am proposing that, and to do for that, I will explain a very simple mathematical procedure. That is only high school calculus. So you guys are very high professionals in mathematics might think this is trivial. And so the difficult part is not mathematics, but it is in physics. But here I'm presenting to you some aspect of that. But before that, because you may not be that familiar with the quantum information processing, so I'm going to present some of that. Okay, in 20th century, actually 1899, before 20th century, the director of US Patent Office, Duell, his name was Duell, and he said, now everything that can be invented in the world has been invented. But in that year, 1899, Max Planck discovered quantum mechanics. And then quantum mechanics became the tool of inventing so many things in modern technology, especially quantum information science, laser, this kind of laser, and this computer based on silicon technology, and so on. And 20th century, quantum physics provided the only hardware aspect of the information science. And so quantum physics with the information science, like von Neumann and Turing and also Shannon, and this information science together made a big information technology community. And it really transformed the whole world. Now, what I'm going to present here is the quantum physics now in 21st century is not only provide not only hardware like laser or silicon technology, but also the software and operating system for whole information science. So when we talk about the information science, now the principle of nature, quantum mechanics is going to be used for everything. So especially quantum mechanics, the superposition principle, the quantum parallelism is due to the superposition principle. And so because of this, quantum computing is exponentially larger and faster than digital computing. So there are some applications like quantum Fourier transform, quantum database search, and also in nanotechnology, the quantum many-body simulation. That may be done only by the quantum computer. And also, quantum physics has some different scheme of measurement than the classical physics. There's no clonability. In digital technology, we can copy everything, any digital information, but quantum information cannot be copied. That no clonability or irreversibility of quantum measurement provide a quantum cryptography. That is absolutely secure digital communication. And also in quantum mechanics, the quantum entanglement, that is a correlation that cannot be mimicked by classical physics. That can provide us with quantum teleportation and quantum superdense coding, and also quantum cryptography and quantum imaging. So many interesting things. And also the one famous physicist, John Archibald Wheeler, now he wrote his last book called Jaewan Black Holes and Quantum Foam. He mentioned his life in this manner, that I think of my lifetime in physics as divided into 3 periods. In the first period, I was in the grip of the idea that everything is particles. That is a classical era. Then I call my second period, everything is field. That is after he learned quantum mechanics, that everything seems to be fields. Then in 1980s and 90s, now I am in the grip of a new vision that everything is information. So maybe your topic is very important, but I am asking you whether you might work on the not just a digital, this real space, but also in the quantum information space. Okay, Korean people are not that estranged from the digital ideas. This Korean people, 5,000 years ago, already played with the bits, and we play with this kind of thing. It's a bit, wooden block, wooden rod, and this is interpreted as a 1, and this is a 0 and 1 and 1, and so we played with this for thousands of years. That's maybe why we are so strong in information technology in Korea. And also Korean national flag, if you could see these things, these bars around the flag, actually this represents a 1 and this represents 0. So they try to represent the universe with the 1s and 0s. But I'm talking about here, this guy is not just a 0 or 1, this is a superposition of a 0 and 1. So it's similar to Qubit, and you can see this looks like a Q, right? And also just before the 21st century, the Business Week journal, they published a special in 1999, August 30th, and they picked 21 key ideas for the 21st century. And here you can see money, demographics, education, politics, and so on. Then number 21, that is quantum computers. There they said the toughest problems will be solved with the roll of the dice. That means roll of the dice. This is a very famous expression that Einstein said in dissatisfaction with the probabilistic nature of quantum mechanics. So he said, God does not play dice. So now this became the symbol of quantum mechanics. And so this is the vision of quantum mechanics, a quantum computer. So quantum information processing, in algorithm, we have a simulation of quantum many-body systems and the factoring large integers that might have applications in information technology, and also database search that might be used for biotechnology. And in quantum communication cryptography, and several months ago, the Chinese group, they said they did around 100 kilometer quantum teleportation realized. And also then about a few weeks later, Austrian group said they succeeded in teleporting 147 kilometers. So it develops very, very rapidly these days. Okay. And for classical computation, Hilbert talked about the 23 most challenging mathematics problems, and in this poor physicist's translation, is there a mechanical procedure by which the truth or falsity of any mathematical conjecture could be decided? Is that correct translation? Okay, I have to be careful in front of mathematicians. and then Turing picked up this problem, and he translated conjecture into sequence of zeros and ones. And read-write head is a logic gates, and this became the model of modern computers. And this is the Turing Machine. So here we have infinite long tape as a storage, and this finite state machine read and do the calculation and record and move and so on, everything based on 0 and 1 bits. So we have this bit and logic gates, and then there's a complexity problem, the P, MP, this kind of problem. But everything it depends on the digital or this conventional information technology, the classical information processing. Then if we have a new kind of information processing, then this complexity class should be transformed. So in quantum information, compared to this digital information, bit 0 and 1, qubit is the linear superposition of 0 and 1. So if we have n bits, then it can represent the 2 to the n states, but very importantly, one at a time. So if we have parallel computers, then we can do at best, we can do linearly parallel computing. So if we have 1,000 computers, then maybe computation time might be reduced to 1,000th. That may be the best. But in quantum computer, if we have n qubits, then because this can make a linear superposition of 2 to the n states at the same time. So it can make an exponentially parallel computing. So here it is the digital idea will give you at best linear parallel computing, but here it can give you exponentially parallel computing. So David Deutsch called it quantum parallelism. But there's a catch. When you extract the result of calculation, you cannot get all of them. You can get only n bits. So here the picture. If you have a digital computer, the input n bits, throughput like this. Okay, this is strange. And then the n bits. If you have a parallel computer, here the throughput will be just a mn. And here, quantum computer and quantum parallelism, it starts with n bits. It ends with n bits, but in the middle, throughput might be 2 to the n, exponentially large the computational space. Okay, so we have some very good ideas on quantum algorithms about the Feynman suggested simulation of a quantum physical system, especially many-body problem. And Peter Shor presented factoring large integers. Here, this is a classical, almost exponential, super polynomial time, but here in quantum computing, we have just a polynomial time. And Grover search algorithm, well, in classical idea, it's the linear scaling, but here it is a square root of n. Okay, so the quantum gates, that is different from the digital ones. Here, it is from the time-dependent Schrödinger equation, and this is also reversible unitary transform. And here, because this one works on bits, here this is a very interesting one, Hadamard, and this one changes the 0 to this 0 plus 1 superposition, and 1 to 0 minus 1 superposition. And this is the simplest discrete Fourier transform. So I'm going to generalize this with a Qudit. So if you use Hadamard Gate on these zeros, then it changes 0 plus 1s. And this, if you expand this, this is a 0, 0, 0, 0, 0, 0, up to 1, 1, 1, 1, 1, 1, 1. So by applying this Hadamard Gate on this input, you can make 2 to the n, the superposition of 2 to the n states. Okay, let me skip this. And also there are an important idea in quantum information, quantum mechanics, that is entanglement. And actually in 1935, Einstein with Podolsky and Rosen presented an article that it said that Einstein did not like this probabilistic nature of a quantum mechanical interpretation. So here, some particle decays into two parts, and one goes to Alice and the other one goes to Bob. Then this situation can be represented in this manner. There are two possibilities. When Alice got 1, then Bob gets 0. Or, with this is one possibility. There's another possibility. When Alice got 0, Bob gets 1. So these two, if there are just these two possibilities, then this cannot be represented as a function for A, function for B. So this is not separable. Then this kind of state is called entangled, because when Alice measures her state and becomes 1, then Bob's result will be definitely 0, and Alice's result becomes 0, Bob's results will be definitely 1. So these two, the measurements are correlated, and there were some trial to explain this phenomena with local hidden variables, but it did not work. And indeed, in 1980s, the French physicist Aspect experimented, and indeed, this quantum mechanics is non-local. Even though Alice and Bob, they are separated very far away, the measurement results are correlated. So I want to skip this part, and so, okay, the same thing. And Charles Bennett, who invented the quantum cryptography and the quantum teleportation, once expressed this entanglement in this manner, analogy. In 1960s, in the 90s, the hippies, they said, I don't know what I think, you don't know what you think, but we know what we think. This is a correlation. So, entanglement can be made by the qubit, the 2 qubit gates. In this case, the one qubit is in A0 plus B1 state, and the target qubit is in 0 state. If you operate this control knot, what control knot does is when the control qubit is 0, you do nothing on the target. But when the control is 1, you flips 0 to 1, 1 to 0. So then after this, it becomes A00 plus B11. So this is not the product state of these two qubits, but they are entangled. And you can entangle one more in this manner. And using this one, this entanglement, you can do the teleportation. I want to skip this. Okay. So this control knot is when the control is 0, you do nothing. It's an identity on the second one. When the control is 1, you operate X. That means 0 to 1, 1 to 0. The matrix representation is like this. Now, actually this control knot can be used for copying information in digital logic. When this is a control and this is target, and when X comes in here and 0 is provided in the second qubit, at second bit, when this X, if you do the X plus Y, the addition into the binary, then this becomes X and X. So this is a copy. But here the condition is X should be only 0 or 1, right? So then you can copy. How about if we use the same thing for the quantum circuit, what would happen? If you use this A0 plus B1 and 0, then would it copy like this? No, this was not like that. It was A00 plus B11. So this is entanglement, not copies. So this is called the no cloning theory. In quantum information logic, you cannot copy arbitrary quantum information. So this was a kind of surprise to people in 1980s, and before that, actually, there was some rumor. If you use quantum mechanics, you can send some signal, some information to anywhere faster than light. But to do that, you should be able to copy quantum information. There is an algorithm how to do that. Okay, this is how to do the faster than light communication. And but if a known quantum state can be cloned, there's a big problem. The 20th century physics, two pillars, quantum mechanics and special theory of relativity, both of them will collapse. Because if quantum states can be copied, then you can copy, make many copies, and you can measure, and you can measure a certain quantum state as accurate as possible. That is against uncertainty principle. And also, if you can copy quantum information, then you can really do communication faster than light. That is against special theory of relativity. So this has a big, deep connection between quantum mechanics and special theory of relativity. And even Steven Weinberg, who got the Nobel Prize in particle physics, did not know this thing in 1990s, actually. So he did the question, can quantum mechanics be nonlinear? And experimentalists said, no, not so positive result. Then two physicists came, Polchinski and Jisang. If quantum mechanics is nonlinear, then communication faster than light is really possible. So linearity of quantum mechanics and special theory of relativity are deeply connected. with each other. Okay, this is a kind of introduction to quantum information science. Now I'm going to do the Qudit. So in quantum computing ideas, we have basically two ideas. The one is molding a quantum state. You prepare an initial state, then you operate some certain gates like this, and like the single qubit gate, the two qubit gate, and so on. Then you manipulate the initial state, then you prepare a final state, then you just measure it. This is one way of doing quantum computing. Then there's another one that is sculpturing a quantum state. You prepare a big entanglement. I told you about the entanglement. It has a correlation from here to there. And that is called a cluster state. How can you prepare it? We initialize each qubit as a 0 plus 1 state. So here I represent them as plus. Initialize each qubit in plus state. Then you do the control Z. This is slightly different from the control not. That is, if the control is a 0, you do nothing on the second one. But if the control is 1, you change the sign plus to minus, minus to plus. So then if you operate the control phase operation on neighboring state, then everything becomes entangled. Now you prepare this thing, and we call it cluster state. Then you measure one by one, then quantum computing is done. So here, in the initial stage, you need 2 qubit gates. But afterwards, only you have to do is only measurement of a single qubit. Now, let me show you a little bit about this control Z and this plus state. Control Z is very useful because these are commuting with the other control Z's. And this is symmetric with respect to control and target. And this plus state is because it is a 0 plus 1 over square root 2. It's even superposition of computational basics states. Even superposition. That means the coefficient of this 0 and coefficient of this 1 are same. Then if we operate this control Z, then control is 0, you do nothing on the second one. But when the control is 1, you change the sign plus to minus. So this is a 0 and plus, this plus state. And this is 1, and this is called minus state. And this is a entangled state, so-called Bell state. And if you do this once more, then you can prepare something called 3 qubit entangled state called Greenberg-Horn-Zeilinger state, GHZ state. Now, let's go to high school calculus. And this is an exponential function, Taylor series. Now, if I divide them into D terms, and I collect, in each group, I collect the first ones. 1, x to the d over d factorial, and here x to the 2d over 2d factorial, and so on. I call them f0x. And second ones, this one, and this one, and this one, and I call it f sub 1x, and so on. Then I might have d such terms here. Then f sub k of x can be represented in this manner. Then, okay, f0x is like this, f1x, and so on. When x goes to infinity, all these polynomials, f sub l of x over e to the x, all they go to 1 over d. So when I first discovered this, okay, should I call it discovery? But anyway, I told this to some of my mathematician colleagues, and they said, really? And it's really like that. And the accuracy is like this. And Then using this fact, I can construct a conjugate relation like a Fourier transform. And this is a polynomials, and this is omega is dth root of a unit in complex space. And this polynomial and this exponential functions have the conjugate relations. So I'm going to use this for physics. An interesting observation of a coherent state. Actually, this is a laser beam. Okay? When the laser comes out, laser light is described by this manner. Here, this n is the photon number. That means this laser light, if you measure how many photons in this laser light, then it could be 0, it could be 1, it could be 2, it could be 3, it could be infinite. But there is a distribution. It is a Poisson distribution. But this is a square root of the coefficients are square root of that. So if you square this alpha, this thing, then it becomes really exponential function. So I can do the similar operations. I divide them into d part, and I call this k sub tilde like this. So this k sub tilde state might have k photons, or k plus d photons, or k plus 2d photons, and so on. And then these states are normalized in this limit, okay, with this accuracy. So this bracket over d, then this goes to 1. And so, and also different photon number states, they are all orthogonal to each other. So in other words, this is an orthonormal basis for this coherent state. So then I can make the two representations, two basis sets for this laser light. So this k sub tilde, this is basically k sub tilde, and sub tilde is basically pseudo-number states, and I'm going to use it for computational basis. So it's similar to 0 or 1 for qubits. And that is even superposition of pseudo-phase state. This is a pseudo-phase state. So these two are in discrete Fourier transform relations. So in laser, here we call this a quadrature space. And in quadrature space, these blobs are representing coherent states. And the distance from the center origin is a kind of a photon number state. So these two are so these guys are phase state. And so you can understand that as an angle. The angle of this state. And this radius, you might understand that as a distance from the origin. That is related to photon numbers. So these two are in conjugate relations. Then, because I can do this with an arbitrary integer d, and okay, let me compare this with Qubit and Qudit operators. The X operator is it flips a 0 state to 1 state, 1 state to 0 state. So this is like this, and Z operator is when when it is 0, it is just 1. When it is 1 state, it is -1. And control NOT is like this, and control Z is when the control is 0, it does nothing on second one. When the control is 1, it does flip only this one. So this representation is like this, and Hadamard is given here. Now, d-dimensional generalization is like this. So if the first off-diagonal elements are 1, and this one is this the corner, it is 1, but Z operator, this is 1 in the on diagonal, it is 1, omega, omega squared, and so on. All others are zeros, and here omega is the dth root of a unit. And this is a z operator. So these are single Qudit operators. Now, we need two Qudit operators. This is a control z. And when the control is 1, you do nothing on the second one. So it's or z operator to the power of 0. If the control is 1, z to the 1. Control is a 2, z to the 2, and so on. So actually, this operator is very important in quantum information processing. And this Hadamard is nothing but a discrete Fourier transform. And this discrete Fourier transform changes from the under tilde basis to super tilde basis change. And actually, these are the physically very meaningful ideas, but they may be rather irrelevant to you mathematicians. And I summarize some of the operator relations. Hadamard Z, Hadamard dagger gives you X operator. Hadamard dagger Z, Hadamard will give you X inverse. And Hadamard will give you this kind of operator that is reversing order in pseudo-number states. And this is a summary of these operator relations. Then, the physically mostly important part is this one. Whether I can realize this operator, control Z operator. Actually, you manipulate single qubit or single Qudit. That is the easy part. Okay, but two Qudit operator that you should interact these two qubits, two systems. That is the most important part in quantum computer. And this operator, so operating on two qubits, this is important. And the big question for physicists has been how to realize this thing. And I'm proposing this can be realized by cross-Kerr interaction between two photon beams. That is, the dynamics is simply proportional to the photon number of the first beam and the photon number of the second beam. If you have this kind of interaction, then you can realize this thing. And operator, if this is a Hamiltonian operator, then dynamics is given like this, e to the I times this Hamiltonian. Then this N1 and N2, these are photon number operators. They are going to pick up the photon numbers from the first beam and the second beam. So the alpha coherent state, this laser light can be usually represented by this the coherent state, that is even superposition of pseudo-number states. Then this N1 will pick up this photon number K. How about the K plus D? K plus D will give you, K will survive, but D, that will cancel out with this denominator, and e to the 2 pi I is just a 1. So this is the magic of this Qudit language. So K plus D photons will give you the same phase change as a K photons. And K plus 2D photons will give you the same phase change with the K photons. So this now the Qudit, the invention works in that manner. Then this is nothing but discrete Fourier transform on either on this one or either on this one. So by operating this cross-Kerr nonlinear interaction on two coherent beams, this kind of laser light, you can get maximal entanglement of first one and the second one, either pseudo-number, pseudo-phase state or pseudo-phase, pseudo-number state. So now we have maximal entanglement of these two laser beams using this simple nonlinear interaction. Now, the question is, now I have to go to experimentalist. Can you make this? So I'm searching for experimental physicists to do that. So if you then, now if I have many of these laser sources, then operate these control Z's between on neighboring laser lights, then I can make this big Qudit cluster state. After that, all I have to do is operate on individual laser beams. Now, here is a very interesting thing called tailoring. So if you measure, after this making a cluster state, if you measure on any laser beams by Z operator, then it kills this guy by measuring this one. Then it's like from this kind of a network, you kill this one. So this operation works as a scissors. But if you measure these guys with X basis, X measurement, then it is like a stitches, like you connect these two by measuring this in X basis. So by these scissors and stitches, you can tailor this thing. And also you can do the quantum teleportation. Here I have some arbitrary unknown state, and here I have a laser coherent state. Then if you operate this thing, this control Z on both, then you measure this one in pseudo-phase basis. The formulation is given here. So if you operate control Z on two guys, then you will get this kind of state. Then you measure the first one in the pseudo-phase basis, and if the result is K, then this result becomes like this. That means by measuring, by doing operating control Z and by measuring the first one, the initial state is already transferred to here. This is a one-step teleportation. If you do this once more, then this measurement result K and S and this initial state are reflected on the third one. So in this manner, you can teleport. You do not move it to here, but you teleport to this line. So this is called a d-dimensional teleportation. And this one is, okay, this may not be interesting to you. This is how to do this phase measurement. This is a phase measurement scheme, and this is so-called, I'm using homodyne detection. And also I can do the conjugate basis measurement, that is for pseudo-number measurement by operating control Z on the Qudit to be measured. If you do measurement here, then that is the same equivalent to measuring this one in pseudo-number state. Okay. Then this is a one-step teleportation, and okay, I'm sorry. And then quantum repeater, we can make a quantum repeater, 5 minutes. So these days, quantum communication, the quantum repeater is very important. If you want to send some certain quantum state from here to far away location, then our digital technology is very efficient. You send some signal through the optical fiber, and if the signal weakens, because the photons might be absorbed on the way, then you can amplify it. You can just copy the same state again and again. Copy. That means you make same guys, many copies. then you can, that is called amplification. So you can send, so there is no problem. But as I told you, quantum information cannot be copied. So you cannot use amplifier. Then how can we send a certain quantum information to faraway location? I have to teleport that. Now I told you about this entanglement of qubits. So then entanglement network, that is a cluster state network. Then using this one, and if you measure in the middle, then you can teleport one qubit state to faraway location. So in this case, if you have a 3 qubit, if you measure this middle one, then this state and this state, the final one, the terminal ones are entangled. So you can use it for teleportation. And for 4 qubit series, then measure in the middle, and the terminal ones are entangled. And 5 qubits also same, then the terminal ones are entangled. So you can send your quantum state to anywhere. Okay, I want to skip this. So when I started this quantum information processing, I invented a word. Do you know this word? I made it up, quantum information processing unit. Then I looked up this word in dictionary. I did not expect to see this word in dictionary. 1977 Webster Dictionary, college dictionary, it has this word. That has even the pronunciation, kipu. Now you might know. This is a device consisting of a cord with knotted strings of various colors attached, used by ancient Peruvians for recording events, keeping accounts, etc. So it looks like this. So here, this is a kipu, and they used it for, these are Peruvian information processing unit for communication and computation. So we are using quantum information for communication and computation. So they use the same purpose. So quantum parallelism, quantum no clonability, and quantum correlation, quantum entanglement. This can be done using the Qudit ideas and entanglement. So here, optical coherent state can be interpreted as an even superposition of d-dimensional pseudo-number computation basis, and control Z can be implemented using cross-color interaction. And I showed you d-dimensional teleportation and the network for quantum communication. And this might be used for Qudit cluster quantum computation. Thank you so much.